take a book and burn it. The book is gone, right? Well, not according to laws of physics. If you could painstakingly collect every particle of ash, smoke, and light, you could, in theory, reconstruct the entire book, every letter, every word. Now, this is because one of the most fundamental rules of our universe is that information can never be destroyed. But for 50 years, there was an object that seemed to violate this rule in most extreme way possible, a black hole. And this wasn't just a small problem, it was a crisis that threatened to break all of physics. It meant that either our understanding of gravity or our understanding of quantum mechanics, the two pillars of modern science, was fundamentally wrong. The resolution to this paradox, the key that saved physics, might be the simplest thing you could imagine: a single number, a half. To understand the crime, you first need to meet the two lead detectives. At one side, we have Albert Einstein's general theory of relativity. It's the law of the large, the theory describing gravity as the elegant bending of space-time. It's what gives us black hole, regions of space-time so warped that nothing, not even light, can escape after crossing the point of no return, the what we call as event horizon. According to relativity, a black hole is a simple beast. After something falls in, the black hole's exterior only remembers three things about it: the total mass, its spin, and electric charge. Now this is called as no-hair theorem, the idea that black holes are bald with no complex features to hint at what they have eaten. On the other side of the investigation is quantum mechanics. This is the law for small, the wild rulebook for the world of particles and fields. And it has one absolute, unbreakable commandment: information can never be destroyed. This means the unique quantum state of every single particle has to be conserved. It can be scrambled, rearranged, or hidden, but it can never, ever be deleted. The information in principle must always be recoverable. For most of the 20th century, the two detectives worked different cases. Relativity handled the cosmos, quantum mechanics took care of the atoms. But in 1974, Stephen Hawking shoved them into a single room, and they immediately started to fight. Hawking discovered something incredible. By applying the rules of quantum mechanics right at the edge of the black hole's event horizon, he found that black holes aren't completely black. It turns out the vacuum of the space isn't empty. It's fizzing with pairs of virtual particles that pop in and out of existence. Usually, they find each other and annihilate instantly. But if a pair appears right at the edge of event horizon, one particle can fall in while other escapes. This runaway particle becomes real, zipping away, carrying tiny bit of black hole's energy with it. To us, this looks like black hole is emitting a faint thermal glow. We call it Hawking radiation, and this radiation has a huge consequence. Black holes evaporate. Over unimaginable timescales, they slowly leak mass until they vanish completely. And this is where the paradox explodes. Now think about it. If a black hole disappears, what happens to the information of everything that fell into it? Hawking's original math showed that the radiation coming out is thermal and random. It carries no information about the unique things that made the black hole, other than its total mass, charge, and spin, just like the no-hair theorem predicted. So when the black hole is gone, the information seems to have gone with it, forever. Now this is the black hole's information paradox. It's a battle of titans. Quantum mechanics screams, information can never be lost, and general theory of relativity, through Hawking's work, seemed to shrug it and say, too bad, I just deleted it. One of these pillars of physics had to be wrong. Either our universe has a delete button, or our understanding of black hole was deeply flawed. To solve this cosmic whodunit, physicists had to figure out where the information was hiding. The first big clue did come from looking inside the black hole, but by rethinking its surface. Back in the early 1970s, a physicist named Jacob Bekenstein was thinking about a concept closely tied to the information: entropy. In one sense, entropy is a measure of disorder. But in information theory, it's a measure of how much information you need to describe a system. A messy, high-entropy system like gas in a room needs a lot of information to describe where every particle is. A tidy, low-entropy system like a crystal needs very little information. Now, it just made sense that a black hole should have enormous entropy. Think of all complex information it swallows. But where was that all information stored? Wittgenstein had a wild idea. Maybe a black hole's entropy isn't related to its three-dimensional volume, but to two-dimensional area of the event horizon. And this was just bizarre. It was like saying all the information in a massive library was somehow stored on its front cover. The idea was so strange that Stephen Hawking himself initially set out to disprove it. In a beautiful twist of irony, that quest led him to discover Hawking radiation in the first place. Once he confirmed that black holes had a temperature, he realized Bekenstein was right all along. The Bekenstein-Hawking formula was born, and it cemented this strange thought: the information lives on the surface. And this laid the foundation for an even wilder concept in 1990s, the holographic principle. It suggests that all the information for a 3D volume of space can be fully encoded on a 2D surface that surrounds it. In this sense, our universe might be just a hologram, just like a 2D plate that can project a 3D image. The 2D event horizon can encode everything inside black hole's 3D interior, so the information isn't inside the black hole in a way we usually think. It's plastered across the event horizon like data on a cosmic hard drive. The surface of a black hole is tiled with smallest possible unit of area, known as Planck's area. Now, each one of these impossibly tiny pixels can hold one bit of information. This was a huge step forward. If the information is on the surface, maybe it can escape as the surface shrinks. Maybe Hawking radiation isn't random after all. What if it's subtly encoded with the information from the horizon? This led to the next big breakthrough, the page curve. A physicist, Don Page, argued that if information is conserved, the entropy of the Hawking radiation can't just keep rising forever. Instead, it should go up for a while, but then, at a point known as the page time, about halfway through the black hole's life, it has to start falling, hitting zero at the exact moment the black hole vanishes. For the first half of its life, the radiation is entangled with the black hole. For the second half, it becomes entangled with the radiation that came out earlier, slowly passing the information back into the universe. For decades, page curve was just a beautiful theory. No one knew the actual physics that would make it happen. But in 2019, a series of stunning papers showed how to actually calculate page curve. By including strange new space-time geometries in their calculations called replica wormholes and islands, physicists were finally able to reproduce the curve Page had predicted. It was a massive achievement. It proved, in the language of mathematics, that information does get out. The two detectives, relativity and quantum mechanics, were finally starting to get along. But a huge question was left hanging. These calculations were incredibly abstract. They told us that information is saved, but they didn't tell us how. What is the actual physical process at the event horizon that encodes information into outgoing radiation? The detectives had proven that the information wasn't destroyed, but they still didn't have the culprit's escape plan. The story of replica wormhole is mind-bending, a trek through the frontiers of theoretical physics. But what if there's more direct idea, one not born from the complex space-time geometries, but from a simple fundamental truth about how information is organized? And this is where we come back to that number, half. While many physicists were exploring wormholes, some started a different path, one looking at quantum geometry of the event horizon itself. Instead of seeing the event horizon as a smooth surface, this model pictures it as a dynamic grid of fundamental units, those Planck scale pixels we mentioned earlier. For simplicity, you can think of them as Planck's triangle, the most basic possible shape you can tile a surface with. Now here is the clever insight behind this particular model. To store most information possible, these pixels should act like bits of a computer, able to be in an on or off state. This binary pattern is the most efficient way to pack information into a system. And what's the most efficient binary pattern? One where, on average, exactly half bits are on and half bits are off. Now, according to this line of thinking, this isn't just an abstract concept. It has real physical meaning. The theory proposes a fascinating relationship where the average potential energy of these Planck triangles on an horizon is connected to black hole's gravitational potential by a factor of minus c square by 2. That factor of half isn't random. It's the heart of the idea. It suggests that in an information theoretic sense, only half of geometric units on a black hole's surface are active. The information is stored in this perfect binary balance. This seemingly simple fraction has a huge implication. It offers a potential mechanism for how information can be both stored on the horizon and passed to the ongoing radiation. And this is where another piece of quantum law gets interesting. The no hiding theorem, proven in 2007. This theorem basically says that if the quantum information vanishes from one place, it can't just be hidden in the either. It has to be moved completely into another place. Information can't be in the limbo. The half idea gives no hiding theorem a job to do. If the information is written on the horizon to this half on, half off binary code, it's not buried deep inside the black hole. It's sitting right on the surface, perfectly positioned to interact with the quantum phase that creates Hawking radiation. As one particle of the entangled pair falls in, the other one escapes, carrying with it a piece of binary information encoded on the horizon. The information isn't hidden or destroyed. It's just neatly passed from a pixel on a shrinking horizon to a particle of outgoing radiation. This model even leads to some new, untested thermodynamic formulas for black holes. One of such proposals connects the black hole's energy E to its temperature T with another famous number, pi, through a fraction pi by 2. Now this isn't just a standard textbook formula, but a specific prediction of its geometric approach, attempting to build a new bridge between the geometry of space-time and the thermodynamics of information. In this view, the solution to information paradox isn't found in exotic, universe-spanning wormhole, but in a simple, elegant rule for the smallest unit of space. Maybe the key wasn't some new undiscovered physics, but a fundamental physics of information itself, staring right us in the face. The beautiful efficiency of number half. So is that it? The case closed? One of the greatest mysteries in physics really solved by the number half? The answer, for now, is tantalizing maybe. Let's be crystal clear. The idea that black hole information paradox is fully solved is not the consensus in the physics community. At all, it's more like detective story where several very convincing suspects have been identified, but the jury is still out. On one hand, you have powerful mathematically solid breakthroughs with the Page curve and replica wormholes. This approach, coming from the world of string theory, has convinced many physicists that information is, without a doubt, saved. It provides a mathematical framework that works, even if the physical picture of the island and wormholes connecting the black hole's gut to the radiation outside is still baffling and fiercely debated. On the other hand, you have elegant and intuitive ideas centered on the fraction half. It suggests a direct physical way of information to get out, based on the fundamental rules of quantum information and geometry. It paints a picture of a black hole not as a monster, but as highly organized quantum state, a perfect hard drive following simple rules. And these aren't the only suspects. Other theories are also in the running. The fuzzball idea suggests black holes have no event horizon at all, but are instead ultra-compact balls of vibrating strings. Loop quantum gravity proposes that collapsing stars form Planck stars, which eventually bounce and release their information. And there are even more radical ideas like firewalls of pure energy at the event horizon that would incinerate any information, forcing us to rewrite some of the Einstein's most cherished principles. Having so many competing theories doesn't mean we are lost. It means we are on the verge of a new understanding. The information paradox has been the most productive puzzle in the theoretical physics for half a century. It has forced us to smash our two greatest theories together and has become a guiding light in the search for a unified theory of quantum gravity. The debate over how information escapes a black hole is happening right now in papers and at conferences around the world. These different ideas, from complex wormholes to simple fractions, are all part of the messy, exciting process to solving a cosmic mystery. So, what do you think sounds more convincing? The mind-bending geometry of space-time island or the beautiful simplicity of a single number? Let us know your thoughts in the comments. And if you want to dive into another puzzle that breaks our understanding of the cosmos, check out our videos in the mystery of dark energy right here. Make sure you subscribe so you don't miss our next journey into the biggest question of the universe. We started with contradiction that threatened to break physics, a cosmic delete button that defied the laws of quantum reality. The journey to fix it has taken us from the mind of Stephen Hawking to the holographic edge of the universe, and from the bizarre space-time wormholes to startling simplicity of a single fraction. While we may not have the final page of this story written yet, we are more certain than ever about how it ends. The information is not lost. The universe does not delete its past. The fact that a number as simple as half could even be candidate for solving such profound question is the testament to the beauty of physics. It reminds us that sometimes the deepest secrets aren't locked away in the impenetrable vaults of complexity. They might just be waiting in the elegant patterns and simple rules that govern everything. The investigation isn't over, but for the first time in 50 years, we are confident that the story of our cosmos, written in the language of quantum information, is a story that will never be erased. Thanks for watching.